Hello, today we'll guide you through the process of training a model to detect defects in your chosen material. For this demonstration, we'll be using aluminum parts as our example, focusing on identifying scratches. Before we begin, it's essential to ensure that the data is clean and usable. We start by verifying that all images are intact and the aluminum parts are clearly visible without any distortions. For this example, we're working with 27 images. However, the number of images you'll need may vary depending on the complexity of your specific problem. Next, we'll annotate the scratches using CVAT, a tool designed to streamline the annotation process. Accurate annotation is critical. Be sure to label all visible defects and maintain consistent annotation rules across all images. Consistency is key to achieving a reliable training dataset. Once the annotation is complete, we perform a thorough review to ensure no defects have been overlooked and that there are no mistakes. Missing defects could lead to inaccuracies during the training phase. After completing the review, we download the images along with their corresponding segmentation masks. These files will serve as the foundation for the model training process. After downloading the images and their annotations, the next step is to divide the data into training and testing sets. Since we are working with a small data set, we will assign the first 22 images to the training set and the remaining 5 to the testing set. To organize the data, we first create two main directories, train and test. Inside each directory, we then create two subdirectories, photos and annotations. Once the directories are set up, we copy the first 22 segmentation masks to the train annotations directory and their corresponding 22 images to the train photos directory. Similarly, we copy the last 5 segmentation masks to the test annotations directory and the corresponding 5 images to the test photos directory. It is crucial to ensure that the segmentation masks in the annotations folder match the images in the photos folder. Any mismatch could lead to errors during model training. And now we will demonstrate how to train a model using this prepared dataset. To begin training the model, navigate to the Neural Network Trainer window. We start by setting the learning rate to 0.01, the batch size to the default value, and the number of epochs to 15. As shown, the model will be trained using a graphical processing unit. However, if no GPU is installed, the model can still be trained using the CPU, although this process will be slower. Next, we select the training and testing directories we prepared earlier, along with the directory where the trained model will be saved. For this example, we'll use the default name for the model. Once everything is set, we click on the Train Model button to initiate the training process. The application will first use the segmentation masks to divide the images into 128x128 tiles. It will then train a classification model to detect defects within these tiles. During training, you'll see accuracy and loss graphs dynamically updating in the training results window. Additionally, the application will display some detections below the training history graph, offering a preview of how the model is learning to identify defects. As we can see, the model has trained successfully. This is evident from the fact that the validation and training accuracy values are closely aligned and remain above 0.9. Additionally, the loss graphs consistently decreased throughout the training process, further confirming the effectiveness of the model's learning. With the training complete, we navigate to the inspection window to evaluate how the model detects defects. In the Classification Models section, we click on Add Model and select the ONNX model file saved during the training process. Next, we proceed to the File Iteration window. Here, we select the testing sample from our source directory. After enabling the auto playback option, we press play to begin the inspection. In the image viewer, we can observe the regions that the model predicts as defective. In this example, the model performs well, accurately identifying defects. However, as mentioned earlier, the results may vary depending on the specific problem and the quality of the data used during training. And this is how you can train, evaluate, and deploy a defect detection model using EasyODM. From data preparation to annotation, model training, and performance evaluation, we've covered all the essential steps. We encourage you to experiment with different datasets and model settings to find the optimal solution for your specific needs. If you found this video helpful, please like it so we know that these tutorials are useful, and best of luck in your defect detection journey.